Welcome back to the Deep Dive. Today we're getting into something fascinating, a really tricky problem in geophysics and engineering.
Yeah,
How do you actually model what's happening inside a fluid-filled crack?
right.
We're talking about Krauklis waves. These are pressure waves moving through fractures filled with fluid.
Yeah, and they pop up everywhere.
Exactly. Think magma moving under volcanoes, water in glacial crevasses, and maybe most critically for industry, hydraulic fracturing in oil and gas.
Definitely.
So our mission today is to unpack why simulating these things in 3D has been such a headache, computationally speaking.
A massive headache.
And look at how a new approach, something called the Generalized Finite Element Method, or GFM, is, well, maybe finally cracking the code.
It's a really promising step forward. You know, the core issue is just how tightly everything is connected.
How so?
Well, you've got the solid rock around the fracture and the viscous fluid inside it, and they're interacting really, really strongly. It's a classic fluid structure interaction problem. But then you add in the scale issue. You're looking at maybe a huge reservoir, kilometers across, but the fracture opening itself, millimeters wide.
Wow, that's a huge range.
It is. And capturing that detail, especially near the fracture front, the very tip of the crack, is absolutely crucial. If you get that wrong, the whole simulation is off.
All right, let's maybe back up slightly. Krauklis waves themselves. For someone who hasn't heard the term, what are we picturing?
Think of them as guided waves. They don't just blast through the rock, and they're not simple waves in the fluid either. They travel along the fracture interface.
Okay, like along the walls of the crack.
Exactly. And they're known for being pretty slow and also highly dispersive, meaning their speed depends on their frequency. Low-frequency waves travel at different speeds than high-frequency ones. Imagine maybe sound trying to go down a really narrow, squishy, pressurized tube.
Gotcha. And the speed depends on that connection between the fluid and the rock.
Critically so.
Yeah.
It's all about how the fluid pressure pushes on the rock walls and how the rock deformation squeezes the fluid.
So why are these slow dispersive waves so important for something like hydraulic fracturing?
Because they're like a diagnostic signal. In oil and gas, you really want to know the final shape and size of the fracture you created. Did it go where you expected? How long is it? How tall?
Right, you need to know what you actually achieved underground.
Precisely. And when you send pressure pulses down the wellbore, maybe deliberately for testing, or even accidentally, like a water hammer effect,
Yeah.
those pulses generate Krauklis waves in the fracture. These waves bounce off the edges, the tips, any changes in geometry.
Ah, so they carry information about the fracture's shape back to you.
That's the idea. If you can simulate how these waves should behave in a fracture of a certain size and shape, and then compare that simulation to the pressure signals you actually measure in the field.
You can figure out the real geometry.
Yeah.
Like matching fingerprints.
Exactly. It's an inverse problem. Use the signal to deduce the source shape.
Okay, which leads us straight to the 3D problem. You mentioned scale, but historically people often used simpler 2D models, right? Like assuming the fracture is just a flat plane.
Yeah, 2D plane strain assumptions. Basically treating the fracture as infinitely long in one direction or having a very uniform cross-section.
Why is that just not good enough?
Because real fractures aren't like that. They have finite length, finite height, variable width. They curve, they might branch. They're fully 3D objects.
Especially in oil and gas, you often get fractures that are much, much longer than they are tall, right?
Absolutely. That aspect ratio is often huge. And a 2D model just fundamentally can't capture the physics of how waves behave in that kind of elongated 3D geometry.
So if your model geometry is wrong,
Your interpretation of the field data, your diagnosis of the fracture is going to be wrong too, maybe significantly wrong. You need 3D for realistic answers.
okay, so 2D is out for accurate work. The challenge then becomes, how do you actually build a simulation tool that can handle these complex 3D cracks efficiently? Especially if you need to test lots of different possible shapes.
That's really where this new research comes in. They developed what's called a monolithic solver.
Monolithic.
Yeah.
What does that mean in this context compared to, say, a more standard approach?
Well, a more standard way to tackle fluid structure interaction, or FSI, is often iterative. You'd solve the equations for the solid rocks movement first.
Okay.
Then you'd use that result as input for the fluid flow solver. Then take the fluid pressure result back to the solid solver and go back and forth.
Iterate until it converges.
Right. But the problem with Krauklis waves is that the coupling between the rock and fluid is so strong that back and forth iteration can become unstable or just take forever to converge, or sometimes not converge at all.
Oh, okay.
A monolithic solver avoids that. It sets up the equations for both the solid, the elastic wave equation, and the fluid, an approximation of the compressible Navier-Stokes equations together in one big system.
And solves everything at once.
Exactly, simultaneously. It's an implicit approach, which handles that strong two-way coupling much more robustly, necessary, really, for this kind of problem.
And within that monolithic setup, they used this Generalized Finite Element Method, GFM. What's the big breakthrough GFM offers here?
I'd say the key advantage, especially for 3D fractures, is about the mesh.
The computational grid you overlay on the problem.
Yeah. Traditional finite element methods, FEM, require that grid, that mesh, to perfectly conform to the geometry you're modeling. So the mesh elements have to line up exactly with the fracture boundary.
Which sounds as a lot of work if the fracture has a complex shape.
It is, and worse, think about inverse problems. You're trying to find the real fracture shape by testing hundreds, maybe thousands of possibilities.
You'd have to create a whole new complex mesh for every single simulation run.
Precisely. A computational nightmare. That's where GFM shines. It doesn't require the mesh to fit the fracture geometry.
Wait, how does that work?
It uses special mathematical functions within the standard mesh elements that cross the fracture. These functions effectively embed the fracture's presence without needing the mesh lines to follow it exactly.
So you can use a simpler, maybe even a regular mesh for the whole ROG volume.
Yes. And you can change the fracture geometry you're testing within that same mesh. It saves an enormous amount of setup time, especially for those inverse problems. It's a huge operational efficiency gain.
That's the mesh independence part.
Uh-huh.
But you also mentioned the physics right at the fracture tip are really important and tricky. How does GFM handle that sharp front accurately?
That's the other clever bit. GFM allows you to build a priori knowledge, things we already know about the physics, directly into those special mathematical functions, the shape function.
Okay, like what kind of knowledge?
Well, we know from fracture mechanics theory that the way a fracture opens near its very tip follows a specific mathematical form. It's called the square root singularity. GFM incorporates that known square root behavior directly into its singular shape functions near the tip. So the simulation automatically captures that critical opening variation with high accuracy.
Without needing an incredibly fine mesh right at the tip, which would also be computationally expensive.
Exactly. It gives you accuracy where it matters most, more efficiently. So you have the solid displacement solved with GFM, and then the fluid pressure and velocities are solved using standard FEM within the fracture domain itself. It all links together in this one big coupled system. They also use specific time integration schemes, NUMARC, for the solid, alpha method for the fluid, suitable for these kinds of wave problems.
Okay, so it sounds powerful in theory, mesh independent, accurate at the tip, but how do we know it actually works? How do they connect this complex simulation to something you could actually measure or use diagnostically?
Right, validation is key. First, they verified it against known manufactured analytical solutions just to make sure the code was fundamentally correct and converging properly.
Yeah, standard practice.
Standard practice, yes. It showed optimal convergence rates. But the real bridge to diagnostics is the fracture transfer function, the FTF.
FTF. Okay, what's that measuring?
Think of it as the fracture's acoustic signature. Technically, it's a dimensionless measure of how easily the fracture takes up fluid when the pressure changes its hydraulic conductivity, essentially.
Okay.
But what's really useful is looking at the peaks in the FTF when you plot it against frequency. Those peaks tell you the resonant modes of the fracture.
Like the frequencies at which the fracture naturally rings or vibrates.
Exactly. The study mentioned example resonant frequencies around 60 hertz, 250 hertz, 510 hertz for their setup. These frequencies are characteristic of that specific fracture's geometry and the surrounding rock properties.
So the FTF translates the simulation output into something directly comparable to seismic or pressure measurements you might get in the field.
Precisely. If your field sensors pick up energy peaking at, say, 60 hertz, you want your simulation of the assumed fracture geometry to predict an FTF peak at 60 hertz too.
That makes sense.
Yeah.
And did they test this against real-world data? Or something close?
They did the next best thing. Detailed lab experiments. They used a block of acrylic, created a fracture in it, filled it with a known viscous fluid glycerol, and then measured how waves propagated through it.
A controlled physical model.
Yes. And they compared their GFM simulation results directly against those experimental measurements.
And the outcome. How well did this simulation match reality?
The paper reported excellent agreement, both for the phase velocity, how fast the waves traveled at different frequencies, and also for the quality factor, or Q.
Q factor. That measures damping, right? How quickly the vibrations die out.
Exactly. So the simulation matched not just the speeds and resonant frequencies, but also how much the waves attenuated, which is really important for interpreting signal strength. That experimental match is huge. It proves the 3D GFM approach isn't just mathematically sound, it's physically accurate.
And that validation really drives home the point about needing 3D, doesn't it?
Yeah.
How did the results compare to those older 2D plane strain models when looking at the same experimental setup?
Whoa, it was a night and day difference. The paper explicitly states the 2D analytical solutions were considerably different from both the 3D GFM simulation and the actual experimental results.
So it's not just a small correction going from 2D to 3D.
Not at all. It's a fundamental shift. Relying on those simplified 2D models, even for a relatively simple planar fracture like the one in the experiment, gives you answers that are demonstrably wrong compared to reality.
That's a really critical finding for anyone using these simulations for real-world decisions.
Absolutely. It underscores why developing these robust 3D tools was so necessary.
Okay, so once they had this validated 3D tool, they could start looking at more realistic shapes, right? What happened when they simulated an elliptical fracture instead of just a simple rectangle?
That's where geometry really starts to show its impact. They simulated an elliptical fracture, keeping the overall length the same as a reference rectangular case.
And
And they found very different resonant frequencies. The FTF signature changed significantly just by changing the shape from rectangular to elliptical, even with the same length.
wow, so the specific curves and corners of the fracture have a major effect on its seismic fingerprint.
It seems so. It means you can't just approximate a complex 3D shape with a simple 2D extrusion or rectangle and expect the wave physics to behave the same way. The interaction between the wave and the detailed geometry is critical.
That makes sense. What about other physical factors, like the inertia of the rock itself, or how sticky the fluid is, the viscosity? Did the analysis give any insights there?
Yeah, a couple of useful points came out. Regarding the solid rock's inertia, basically, how much effect the rock's own mass and acceleration has on the wave.
Uh-huh.
It seems that for many relevant scenarios, especially the lower frequency excitations typical in hydraulic fracturing, often below 100 hertz, you can frequently neglect the solid inertia terms.
Which would simplify the calculations a bit.
Potentially, yes. It suggests that focusing computing power on the fluid dynamics and the elastic stiffness might be more important than fully capturing the rock's inertial response at those frequencies.
Okay. And what about the fluid viscosity? Does making the fluid thicker, like using heavy oil versus water, change the resonant frequencies?
That was quite interesting. What they observed was that changing the fluid viscosity significantly impacted the magnitude of the peaks in the FTF.
Meaning it affected the damping, the Q factor.
Exactly. Higher viscosity led to more attenuation, lower peaks. Made sense. But crucially, viscosity did not seem to influence the location of the peaks, the resonant frequencies themselves.
So the ringing frequency stayed the same, even if the sound died out faster with thicker fluid.
That's what they found in their analysis. It suggests that the characteristic resonant frequencies are primarily determined by the fracture geometry and the elastic properties of the rock, not so much by the fluid's sheer viscosity.
That's a really useful insight for interpreting field signals, too.
It is. It helps separate the effects of geometry from the effects of the fluid properties.
All right, so let's try and wrap this up. What's the core takeaway here? What have the researchers really achieved?
I think the big achievement is demonstrating a robust, accurate, and computationally practical 3D tool for analyzing these complex fluid-filled fracture dynamics.
The practicality being key.
Absolutely. That mesh independence of the GFM is a game changer for efficiency, especially for the kind of inverse modeling that's essential in oil and gas exploration and monitoring.
Running potentially thousands of simulations to match field data suddenly becomes much more feasible.
Exactly. And that efficiency opens doors because GF doesn't really care what the material model is for the rock, and it doesn't need the mesh to fit the fracture. You can start thinking about tackling even more complex scenarios in the future. Things like non-planar fractures that curve in 3D, or maybe even branching fracture networks.
Or adding more complex physics.
Sure, you could potentially incorporate material nonlinearities like plasticity if the rock starts to deform permanently near the fracture, or even model the effects of roughness on the fracture faces. The framework is flexible.
So for you, the listener, what's the final thought here? It seems like we now have tools emerging that can finally get past those old simplified views.
I think so.
It means that the actual, detailed, three-dimensional shape of an underground fracture might be far more critical to its seismic signature, its fingerprint, than maybe we fully appreciated before.
The geometry really matters.
And now we're getting the computational methods needed to actually explore just how much it matters. You now know where the cutting edge is heading in simulating these incredibly complex but crucial underground features.